Okay, hello and welcome back to another one of my video log recording sessions where I talk about genetic algorithms. Well, the date is 2025, June 6th. What time is it? Yeah, 43 past 2 in the morning. That's 2:43. Yeah, let's get right into it. Just 1 second. Okay, so last time I believe I left off with the finding that with the finding that changing population size is beneficial, and to be more specific, increasing population size is quite beneficial as it saves time and tends to give similar results for less computing power, that is. So what it is that just as a brief recap, if I had 100 items, if I had 100 items, if I had 100 items, namely item 0, item 1, item 2, all the way to item 100, and or gene, in this I always use these two terms interchangeably. And if I had that, and if I wanted to find the best combination of items or genes, I could give for the 100 items, I could allocate or start with, or just work with in general 1000 entities, and from the very start, which is usually named generation 0, all the way to the maximum number of generations, in for example maybe 1000 generations. You usually don't need this much, but I mean, I'm still giving an example. So this takes some amount of time. Suppose it takes some amount of time. However, it was quite clear. It was quite clear that for the 100 items, imagine this. This is the list of items. Yeah. And well, imagine this is the list of items, and I divide this into 10 bits, or 10 parts of 10 items, all the way. Let's not do this. Till here is 10 items, until here is 20, 30, all the way to 100 items. And for each additional 10 item, for example, 100 entities were added to simulate the evolution, to carry out the evolution. So rather than starting with 100 items plus 1000 entities, starting with 10 items with 100 entities, and then moving on to, after some number of generations, usually called an era. And in my last video that was 100 generations, 100 Gs. We increase the population size to 200, and then another era would pass, and then we would have 300 entities, and this will continue until we have 100 items, and then we have 1000 entities for this last era, which is again 100 generations. And this takes less time than doing this, because there's far less to compute on the surface. And when I say on the surface, you could think of it as briefly just skimming through a document. Yeah. So what that means is that if, for example, for 1000 generations, for 1000 generations, if I had 1000 entities, just simply multiply both numbers and then you get 1 million. Yeah? But if you had 100 items, 100 entities for 100 generations, that's 10,000. And then it's 200 entities times 100. That's 20,000. See where this is going? So, as opposed to the 1 million, the number 1 million here is going to be 5,500, which is the result of adding 100, 200, 300, and all the way to 1000 times 100. So that's 5, 5, 0, 0, 0, 0. So on the surface, this is, well, 55% less computation. Of course, it doesn't actually, it is not actually exactly 55% of the computation, but you get the point. That, the point being that there's a lot fewer things to compute. So we found out that it's beneficial to do that. And this is probably the last bit or video that I do on this part of dynamic genetic algorithm. It's not the end. It's just that there was, when it comes to dynamic genetic algorithm, or rather doing genetic algorithm in a dynamic way, there were 8 variations. So what was it? It was util values, util vals, and then constraint vals, and then num items. And the first one was all the videos, or the majority of, or most of what I did so far was a setting that we could probably call, well, let me rephrase that, was a setting where the utility values were fixed, the constraint values were fixed, and the number of items were fixed. that's one combination. It doesn't matter if the values are preset or generated or what I call general, but it doesn't matter. Everything was fixed. What I've been doing for the last 2 weeks was where the utility values were fixed, the constraint values were fixed, but the number of items were varying, or they what's a good adjective for varying? Or rather, what's a good word for being the opposite of fixed? Opposite. I'm googling, by the way. No. Do I want to call it flexible, adjustable, negotiable? No. Antonyms, yeah. Indefinite, changeable, flexible, fluid, variable. No, it's just too. No, it's not temporary. Changing, volatile. Volatile is a bit too strong. Adjustable, negotiable, changeable. No. Fluctuating, no. Fixed. Antonym. Nope. Antonyms, yeah. Insecure, no. That's not what I want. Indefinite soft. I'll just stick to varying for now. So anyway, for the last 2 weeks, what I've been doing was fixed, and the utility values were fixed, the constraint values were fixed, and the number of items was the only thing that was varying. So, oh my god. So this we've done. This we have done. What about the rest? The rest is fixed, and then there are 8, obviously, because there are 3 categories that we could either toggle in between fixed and varying. So, for example, the next one would be, or could be, fixed, varying, and then it could be, seriously, fixed, varying, and fixed. So that's 4 of them. Yeah, and then I could have the utility values varying, and then I could have the constraint values varying, and then I could have the number of items fixed. I mean, varying, fixed, and then I could have varying, fixed, and then I can have varying, fixed, varying, and lastly all varying, which I'm sure will be a disaster for me to code. Is this 8 of them? Let me just see. By the way, we're not totally done with this yet. This video will be the last, but let me just see this. Fixed. I think I've covered most of it. We got this. We got fixed, varying, fixed, varying, fixed, varying, fixed, varying, fixed, varying. Yeah, I think we got all of it. So, this we have done. This I'll finish today, or rather in this video. and I would have 6 of these left, which I think as I've with what I've done so far won't take that much time, and I don't think a lot of the things I cover or deal with as I do these 6 will kind of overlap, so that might save me some trouble, but that's still, I'm just guessing. So as this is the final video of this portion, oops, that's not so pretty, of this portion, I'm I've decided to do, or rather get rid of all the questions or qualms or anything that I might have left to ask about this setting. Any other questions that I asked myself? Things like, what would happen if I did this? What if I did that? And would things be different? So yeah, that's what this video is going to be about. So that goes away, and that goes away. Yeah, so I wondered if would the first two quote-unquote experiments weren't actually that crucial, but I wondered what would happen if I added, for example, if I added some void entities, or entities with chromosomes that were full of zeros. For the usually for the purpose of trying to make the entity distribution a bit wider per generation, or for each era, or whatever. So I'm gonna show you that one. This is what happened when I put in when I created void entities per generation, and you can see that because I did that, I have entities here, these like a really long tail. So well, that was fun. So I had a look at the summed utility scores, and now you see this, that the blue line just sits at the real actual bottom, except these few very tiny spikes, and this keeps on happening even when the era changes, and which is obvious because I keep on adding void entities that score that has a summed utility score of 0. But in this case I got a bit lucky, but it is still quite interesting to observe that I still have the maximum ever at what is supposed to be, or what is thought to be, the true ceiling, that is 2865. So it didn't really affect the overall progress of entities in a negative way. So the next thing I tried was I added a random I added entities with random chromosomes, with random genes. Oh, by the way, this is same for the void genes and for these random void entities and these random entities. I added them on top of the newborns that were created through through procreation. So they weren't actually in a way compromising the number of newborns being created per generation. So random entities, random, yeah, and this is what it looked like. See, again, really long tail on the left, but the KDE distribution, KDE kernel distribution, does look a bit prettier now that there are more entities on the left, and they kind of overall stop the entire distribution from crushing itself into this red wall that is the total sum of utility, meaning when the max constraint value is at 100%. But even in this case, the overall progress of entities didn't seem to be compromised, as in the end the maximum error was 2855, so it's only like 10 off from the true ceiling, which, so it was a bit unlucky, but it's not far off, so it didn't have any negative effect. So, and the next thing I did was I removed the parts where I added void entities and random entities, but to be able to compare what I'm about to do next, I went back to one of the default settings where there would be 10 eras and 10 items, where there would be 10 eras, and the first era would start with 10 items with 100 entities in the population, and as the era moves on, 10 additional items would be added and 100 more entities would be added to the population size. And I did that for the purpose of saving all the entity distribution at the end of each era. I know this is tiny, but this is what it looks like at the end of the first era, second era, third era, fourth, fifth, sixth. Now you can see that until the fifth era the entity distribution is very, very skewed, and you'll see that the mode is the true ceiling, which may look good, but I don't think that's good. But anyway, but since the sixth era, we start getting the distribution. We start getting more of the right half of the distribution, as you can see right here. Compare this to here. Oops. Compared to this, where there's almost no right half, because everything just converged to the true ceiling, we start getting more of the right half. Of course, the mode is kind of like the true ceiling now, or the mode is very close to the true ceiling, and now the distribution is more a bit wider, more spread. 8th era, 9th era, final era. This is nothing we haven't seen, but until now I just hadn't saved the entity distributions per era, so there it is, here they are. But I did this because I wanted to do a thing, and by that thing We'll start with very weird ones. So what I'm about to show you is what happened if I just filled up the initial population with the, hold on, what is this? Not this, 1 and 2. What would happen if I filled up the initial population with entities that had the true ceiling chromosomes, and see how they play out over 1,000 generations? This is how it plays out. So you'll see that the top 10% and the head entities just stay there, but the bottom entities kind of fall, and then they just stay there as well. This is also apparent, right, when I have a look at them per 100 generations. But so that's what happens. So even the new evolution scheme does not guarantee that tail entities just fall off quite dramatically, and therefore as a result, this is what the distribution looked like. Which is quite odd, right? Because the entities were given the true ceiling chromosomes, and yet they somehow managed to give us a distribution shape such as this. But however, we do still have the mode being the true ceiling, but you know, kind of amazing that this still happens. But this setting had, well, it was all tested, or rather, the number of items was set to 100 from the very first generation 0, but the population size was set to 100, 200, 300, and so on until 1000. So I wondered what would happen if I set the population size to 1000 from the very start, from the get-go. Well, the same thing happens. And here is the distribution. Well, the funny thing is that the mode being the well, being at the true ceiling, I don't know if that's funny actually, tends to decrease. The highest it's ever been was 73, but over time it does decrease. It does oscillate, but it does decrease, so, which is kind of obvious if you think about it. So even when you do give entities true ceiling chromosomes, given enough time, entities will kind of reverse converge and form this kind of a distribution. Maybe give them 10,000 generations and they'll be almost normal. Well, not that normal, but so those are the two things that I did. Next is where things got quite complicated, but it was fun doing all that. But to do this I need to explain a bit, so give me one second. Okay, so first thing, I'm going to start off with a mouthful. It is called, or rather, I'll just type it. Anything? Any other color? Purple. Random, gradual, inclusive, incremental. 4 adjectives. I know I don't like it, but at the moment I don't think I have a good alternative set of words for this. So again, let me explain. Let's suppose I have 100 items, as seen here. So this rectangle, well, depicts the 100 genes or items that I have at my disposal. Well, not my disposal, but anyway. And until here is 10 items, until here is 10 items, until here is 10 items, 10 items, 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, that's right. So, these are the items, and these are the utility values, and these are the constraint values. I don't really need 3 rectangles or 3 bars, but I felt like it. Oops. No. Oh, they're touching. Oh. Okay. Great. And let me just color, get this one red and this one blue. So and these are the items, and these are the utility values, and these are the constraint values. Okay, and so what do I mean then? And then I'll start from explaining the first word. What do I mean by random? Well, here's how the experiment goes. For random, gradual, inclusive, incremental, R, G, I, maybe RG, I squared. I don't know. Anyway, for random, gradual, inclusive, incremental, what happens is that I pick 10 items out of all these 100 items. I pick 10 items from here, here, maybe here, maybe another one from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I pick 10 items in the first era. So there are still 10 eras. 10 eras. Oops. Okay, fine. And then 10 items will be added per era. So for the first era, 10 items chosen. For the second era, another 10 items chosen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in the second era there will be 20 items, including the items from the first era. From the third era, another 10 items. 5, 6, 7, 8, 9, 10, something like that. So you get how this goes. But it's random because everything is chosen from anywhere and everywhere. It's gradual because the number of items increase by the era. It's inclusive because the items or genes that were previously included, or that were included in the previous era, remain in the next era. It's incremental. So these two words are kind of similar, but anyway, it's incremental because the number of items change. Increase. Again, these two items are also kind of similar, but at this point I have realized that I'm quite bad with naming things, so maybe there's a better word for it. I just haven't looked it up. And while this happens, so by the last era, the 10th era, I would still have 100 items. And for this setup, I was using the same maximum constraint list that was used. So I used the same maximum constraint list that was for the preset values where the order of items were not random or changed. But for the first few settings, I used the same maximum constraint list, which is a list of maximum constraints per era. So I used that, and the purpose of doing this was, does order matter? I wanted to see that. I wanted to see if the order of items or genes in which they were introduced to the evolution matters, in terms of maybe like most importantly the final, or if let me rephrase that, if order matters in terms of how it affects the final true ceiling, because I still don't know yet. I don't think I have a definitive answer yet, but we'll see. Because order might matter given a different set of preset values, but so far TLDR it doesn't seem to. But anyway, which is a good thing, by the way, in its own way. But anyway, so yeah, same max constraint list. The purpose, does order matter? That's what I'm trying to see. And what else do I need to mention before I go on? Yep. And of course, the utility values and the constraints values would be the same, but according to what items were chosen. Okay, cool. So I'll show the results now. Here are the distributions. You see this tiny distribution, but very, very skewed. And then we go on: second era, third era, fourth era, fifth era, sixth, seventh, eighth, ninth, 10th. Quite amazing that now we have a lot of the right half in the 9th era, and in the 10th era this is what happens. And when we have a look at the sum utility scores for the world, second generation, the second era, third era, fourth era, fifth era, sixth era, seventh, eighth, ninth, 10th. No, this is 10th at the end of the final era, and the maximum ever was 2855. So it was a bit unlucky, but it doesn't seem to stray far off from the previous setting. So I tried again, just to see if it was, you know, out of bad luck. Yeah, it turns out it was, kind of. But now it's 2860. So, and the distributions looked somewhat similar. Well, not in this case. But anyway, they did look somewhat similar. Nothing that much out of the ordinary. And the next setting I tried was I made some changes to the max constraint list. Instead, this time the max constraint was some percentage of total constraint of that era. So for example, if 10 items were chosen for, well, 20 items were eventually chosen for the second era at the start of the second era, then the total constraint would be calculated, and a certain percentage of that total constraint would be used as the value for maximum constraint. And in this case, the x, the value x, or the variable x was 18,000 divided by 24,540. And this, why this specific? Well, I still wanted to keep the I still wanted to keep the last maximum constraint for the last era to 18,000, so that I would know if I have the true ceiling, which is 2865. And when given 100 items, the total constraint is 24,540. So times that, I would get 18,000. And when the maximum constraint is set to 18,000, if I have 2865, then it means that I have some entities that have hit the true ceiling. So that's what this is. Here are the distributions, again, quite similar. You can see what era it is at the top. If it's era 7, then it means it's the 8th era, because the first era is 0, obviously. In the 9th era, this is what it looks. Oh well, in the 10th era, the last one, this is what it looks like. Final is the 10th era, but anyway. and the summed utility scores look like this. So we don't know the true ceiling, or rather we don't know if they have hit the true ceiling in between, or rather for the first up until the very second last era. But the only true ceiling we may know kind of more for sure is for the last era, and in the last era we have 2865. So yes, they have converged, the entities have converged, and we're still doing random, gradual, inclusive, incremental. It's just that the maximum constraint list was slightly altered. And I did this 2 more times. I'll quickly show the summed utility scores. So 2855, well, unlucky, but it does seem to be quite similar. We have 2865, the true ceiling, again. So it seems to be working. And for the next setting, what I did was just set the maximum constraint per era to be not this, but 65% of the total constraint of that era, except that the last maximum constraint for the last era is still set to 18,000. Why? Because I want to know if they have converged. So I want to stick to a known value. So it would be 65% times total constraint all the way until from era 0 all the way to era 8, except for era 9 or the 10th era it will be 18,000. Okay, and here are the distributions. Quite similar to what we've seen, and here are the summed utility values. We do have 2865, so they have converged. And I did this for one last time. We have oh yeah, I did this for one last time, except this time it was for the higher max constraint values, where the maximum ever was 3065, which is the true ceiling for this setting. So it does work even when given a higher set of maximum constraint values, or maximum constraints. So, what else? What else can I do? Well, I can do some more complicated things, some more convoluted and complicated things. So, that's exactly what I did. Actually, let me just... Yep. So bye bye. Again, let's do that. We have items, and then we have until 10 items, 20 items, 30 items, 40 items, 50 items, 60, 70, 80, 90. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 10 sections, 10 items each. This is items. This is utility values. And this is constraint values. But this time I changed things so that it is random, it is gradual, but it's not inclusive, it's only incremental. Incremental, is that the right spelling? Yeah. But with an A, just to specify that this is type A. In this case, it is random because the items will be chosen in such a way that in the first era, era 0, about 10 items will be chosen. And notice how I just said about. So because if an item is chosen or not to be considered as if an item is chosen, it means that the genes for the entities are activated. Because in this way, what happens is that an entity will have a chromosome that looks like this. It would either have a 0 or a 1 if the gene is activated. So it could be, for example, it could either have a 0 or 1 if it's activated, or it could have a non-type. And remember, I'm using Python, so it's either non or 0 or 1. So for example, an entity could have a chromosome that starts with 1, 0, non. I'll just write NN 1, 0, 0, 1, etc. You get where I'm going with this. So in order to decipher whether something is activated or not activated, the items per era would have to be chosen. So because at the very start of the evolution iteration, the blueprint, what can be called so as the blueprint, looks like this. This is the same for the previous setting as well, for the random, gradual, inclusive, incremental, but I forgot to mention how it works. But anyway, or not, but yeah, this is how it usually works. You're given 100 zeros, or the equivalent amount to the number of items, so zeros. And at the start of the very first era, this is how it goes, or at the start of any era for that matter. If it's 0, then it has some chance of turning into 1 or being activated. So around 10, I set the ratio so that around 10 of genes would be activated per era. 10 additional genes will be newly activated per era. And if it was already a 1, it could also be deactivated, but at a different likelihood, with a different probability. So activated genes could be deactivated, and deactivated genes could be activated, but in such a way that per era 10 genes would still, around approximately 10 genes will still be added on. So it's random because I'm still picking 10 genes from somewhere. That's 2, 4, 6, 8, 9. I still picked 10 genes from somewhere in the first era. In the second era, this could be gone, and this could be gone. But in the second era, around 10 more. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 could be activated. That's in the second era. So I still have around 20 genes activated. In the third era, it's still the same. Some of them could be deactivated, or even none of them could be deactivated, but still around 10 genes could still be activated. You get the point. So it was set up in such a way that the first era would be responsible for 10 genes, the second era 20 genes, around 20 genes, third era around 30 genes, and so on until the very last era, era number 10, would be dealing with 100 genes, but always 100 genes, because I wanted to set it up in such a way that by the end I would be covering 100 genes, so that I would know if the true ceiling has been met. So it's random because I chose, it's gradual because the changes are gradual, it's incremental because I made sure that the number of genes increased per era, by the era. The only word that's missing, that is inclusive, was left out of this. Oops. Was left out. Was not used because I cancelled out some genes, so it's not really inclusive. So when I do that, this one, random, gradual, incremental, type A, here's what the distribution looks like for the final era. Here's for the first era, second era, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th, the last one. And even for this, I made sure that, where is it? I made sure that the maximum constraint per era was I made a mistake. I made sure that it was 60% of the total constraint of that era. I think I said that it was 65%, but no, it was actually 60%. So again, let's have a look at the distributions from one last time. First era, that's a very weird looking distribution. Second era. Okay. Oops. Third era. Okay. Sorry, my mouse is kind of broken. Fourth era. Fifth. Sixth. Yeah. So still kind of seems like it's working, but let's have a look at the summed utility values. First era, second era, third era, fourth, fifth, sixth, seventh, eighth, ninth, 10th. So we still have 2865, the true ceiling. The maximum ever is 2865, so we have hit the true ceiling. So it does seem to work. However, one thing to note here is that there are always these sharp dips, and this is due to those some genes going deactivated at the start of each era. But then again, because more additional genes have been added, the summed utility value goes up to a certain extent. And then, see, even there's always a small cliff like this one, but even there's a very tiny one here, and there's another big one here, there's a tiny one here. So these sharp dips are because of those because of those genes going deactivated. So I'll show you another one of random gradual incremental type A. The distributions, again, very weird distribution up there, very skewed. Okay, kind of ordinary. First era, summed utility values first era, second era, third era, fourth era, fifth. Is it fifth? Yeah. Sixth, seventh, eighth, ninth, 10th. Again, we do see sharp dips because of those genes being deactivated. But we have the maximum ever at 2860, which is the second highest I've ever seen. That is 2865, the true ceiling. So this also does seem to work. We just got a bit unlucky. And now we move on to the last setting. Last setting that just, you know, that gave me a huge headache. So this one is called not A. Okay, this can go. items. What? No. And so 0, 0, 0, 0, 0, 0, 0, 0, 0, all the way to 0, 0, 0, 0, something like that. What? Why did it just do that? 0, 0, 0, 0, 0, 0, 0, 0, all the way to 0. Better. So, this one is called B, as in type B. Oops. So what this does is it is still random, because I'm still choosing 10 items randomly, but well, in this method, there's no guarantee that items that were chosen in the previous era stays. There's no guarantee. They may stay, they may remain in the next era, but we cannot be certain, because in the first era, that is era 0, out of the 100 items or 100 zeros, I'll choose 10 zeros to be flipped to ones. So 10 ones. In the second era, that is era 1, out of the we come back to the 100 zeros, representing 100 items not yet selected to be activated, but we come back to the 100 zeros, and then we choose 20 zeros to be activated and flip to ones. So now we have 20 ones. In the very next era, era 2, or the third era, we come back again to the 100 zeros, and then we choose 30 genes to be activated or flip to ones. So there is no guarantee that this will stay in the next era, because everything is just going to reset, and the required number of genes will be chosen at random. So yes, the same thing could be chosen, but it's not guaranteed. So it's random, as shown. It's gradual, because things will change gradually. It's incremental, because the number of genes being activated increases by the era. But it's not inclusive, because there's no guarantee that the previously activated genes in the previous era stay. So it's not inclusive. But and it's slightly different from random, gradual, incremental type A, because in type A, I did make sure, or did guarantee to some extent, that previously activated genes stay. So I did that. So in a way, as the eras progress, you could say that it's a totally different knapsack problem, but with more genes activated. So let's have a look. Here's the first era, the distribution from the first era. Again, very weird, but very, because they're very converged. They over converged. Second era, third era, fourth era, fifth era, sixth, seventh, eighth, ninth, and 10th. So the shapes look quite familiar, right? First era, second era, no, this is until generation 120. Second era, third era, fourth era, fifth era, sixth era, seventh, eighth, ninth, 10th. And as you can see, the cliffs are now more dramatic. We have more dramatic, more acute falls, because, like I said, per era it's a different problem space, unless the number of items are big enough so that now the genes that were activated previously overlap or start overlapping with the genes to be activated in the next era, genes that are to be activated in the next era, like for example here. This is when things went from, when the number of genes went from 70 to, from 80 to 90, and the maximum ever in this case was 2850. So even when we are actually presenting the entities with a new problem per generation, per era, in the end it does seem to work. To, quite close, because 2850 is not that far off from 2865, and given all these times when things were actually kind of soft reset, we still managed to hit 2850. And I did this one more time. Here are the distributions. First era, nothing happened, sadly. Second era, third, fourth, fifth, sixth, seventh, eighth, ninth, and 10th, the last one. So, nothing unusual there. Well, the fact that it's nothing unusual is actually unusual, because if you had this kind of series of drastic changes, you might expect some changes in the shape of entity distributions, but that wasn't the case. Here are the summed utility plots for the world from the first era, second era, third era, fourth era, fifth, sixth, seventh, eighth, ninth, 10th. Here the changes or the fluctuations are even more pronounced. But then again, the maximum ever was 2860, so it's not far off from the true ceiling, that is 2865. So that's about it for this is all the plots that I was planning to show in this session, but a couple more thoughts, and one of them is that if they work regardless, and if even with 100 items and 1,000 entities, with 1,000 entities and with 100 items given 100 generations, I'm not sure if I could just reach the maximum, reach the true ceiling given only 100 or 200 generations. But it's actually, I've done that before. All I have to do is look at one of those times when I did everything in one go. So when was that? Let me just look for it. Okay, version 100 each. Lower base mutation rate. I'll just look for it here. Maybe in here. Oh, that's too many. Okay, just give me a second. Yeah, I think this is it. First, sick. Here we go. Really? What just happened? Okay. So this is when I did everything in one go. This is first era, or until generation 100. Generation 200. Generation 300. Generation 400. Generation 500. 600. 700. So it took me about 700 generations to do this, whereas which usually takes somewhat longer than when using dynamic population or varying population change. So I'm wondering if I can achieve convergence, if I can get the entities to converge, if I can achieve true ceiling given 200 to 300 generations using dynamic population rather than doing things in one go. I mean, I don't always have to start from 0. I can start from somewhere here. I could just, well, skip the initial first half, initial parts, and do that. I think that might be the last of this portion of dynamic genetic algorithm. I thought this video would be the last, but I think that should be the last, to see if I can shorten this process on the right, because this process on the right is already short enough, it's already more efficient, but I would like to see if I can just have 5 or maybe at most 5 of the 10 eras and still achieve the same convergence level. Yeah. Okay. Well, that's about it for today. Thanks for watching. Bye.